Okay, so we're going to get started. This is lecture 11, and we're going to start a new topic today, rigid body dynamics. Okay, so up to now, everything we've been doing has been assuming that there's some kind of flexibility in the system, which is represented by the spring. Okay, so now we're going to assume that the elements that we're looking at are rigid. Okay? And so we're going to look at rigid body dynamics, and we'll explain as we go along where the relevance for rigid body dynamics comes in. So we're going to start with a definition. So for a rigid body, the distances between 2 points on the body do not change. We'll draw a sketch in a minute to show how this works. So that means if we can't squeeze or deform or deflect this body, okay? Points that are on it stay the same distance apart. And the second thing is that rotation is constant for all points on the body. So, let's draw a sketch. So the rigid body. Okay, so arbitrary shape. Nothing trouble about it. There's two. I think the microphone's good. So I'll try and use this microphone. Okay, so we've got 2 points on the rigid body, A and B. And we tend to write the distance between them as RAB. Okay, so that's, you'll see in a minute, we'll define these, some of these properties a bit more formally. And the rotation of the body is normally defined as an angular velocity omega. What it means is that the whole of the body is turning at angular velocity omega, okay? So it means that if you imagine this is some object in space, it's a rigid object, it's rotating at an angular velocity, and so the angular velocity applies to all points on the body at the same time. So we'll say that RAB is the distance between points A and B. And we have VB stroke A is the velocity of B with respect to A. And omega is the angular velocity. So just a note about omega. I know in all of the previous stuff we've done, we've used this omega for frequency, haven't we? Okay? But if you look, everything online or every textbook on rigid body dynamics always has omega as the angular velocity. So we just have to be aware that that's obviously a notational clash with what we've had previously. Okay? So normally if you look at any questions in the problem sheets or exam, it's very clear that it's either about rigid body dynamics, in which case omega is angular velocity, or it's about flexible vibration, in which case omega is frequency. Okay? So for rigid body dynamics, we're going to use a vector representation of motion. Okay, so what we're going to do is we're going to have a set of coordinates in a 3D space. And so we're going to define them like this. We're going to have vectors I, J, and K. Okay, so they've got lines underneath them. So the lines underneath mean that this is a vector. And later on, I'll actually write down what the vectors are for these I, J, and K explicitly. Okay, but for now, let's just take it that we have this three-dimensional space made up of these three vectors I, J, and K, and they're orthogonal to each other. Okay, so they're at 90 degrees to each other. So if we want to represent some point in the space, okay, and maybe that point is part of a trajectory of some motion or something happening, okay, what we do is we define a vector from the origin to that point, and that's the vector r, so r with an underscore. So then R consists of three components, okay, and they are X, Y, and Z, and they correspond to the I, J, and K axes, okay? So if we break this down, if we project down from here into this domain, okay, onto that plane, whoops, sorry, I've done that wrong, and then we project that onto this axis here, we have a quantity x along the I vector, y is the distance along the j vector, and z is the distance on the k axis. Okay, so this should all be fairly standard geometry. So if we write down the vector r, okay, so we can write r down like that. So x, y, and z are going to be the numbers which define that point in space. And because we've multiplied them by I, j, and k, we're indicating which direction the vector component is in. So if we differentiate that to get the velocity, we get a velocity vector, v, which is equal to dr by dt, and that's just equal to x dot times I plus y dot times j plus z dot k. And we could do the same thing again to get acceleration. So we differentiate r twice, don't we, to get acceleration, so let's call it r double dot. And of course that will just be equal to x double dot times I plus y double dot j z double dot k. So I'm sure you'll all remember how to use vectors, but we're just going to recap on some of the key properties of vectors. So if we're doing vector addition, that's by component, isn't it? Okay, so vector addition is straightforward. We add the x components together, the y components together, the z components, right, and we get a new vector. Okay, so I don't think we need to stress that point anymore. But vector multiplication is more difficult. And there are two cases, aren't there? The first one is the scalar or dot product. So, for two vectors, u and w, so u is equal to u1i plus u2j plus u3k. W is equal to w1i plus w2j plus w3k. And we can think about these two vectors as having an angle theta between them. So the scalar or dot product is usually written as this: u dot w equals u1 w1 plus u2 w2 plus u3 w3, which is equal to a scalar quantity. And it's also equal to mod of u times mod of w times cos of theta, isn't it? So let's do an example using scalar product to find force component acting along the length of a cylinder. So here's a scenario. We've got a cylinder and the central axis of the cylinder. Okay, we can represent that as a vector. So that's r in some coordinate space. Sorry, that's x I plus y j plus zk. And if we've got a force acting at that point as well, that's a force vector F, which has, again, can be divided into the three components Fx multiplied by I plus Fy times J plus Fz times K. So scalar product of those two vectors F dot R is equal to mod F mod R cos theta, and theta of course is this angle in here. We can see by trig that the component of force acting along length of cylinder is mod F cos theta and so we can use a trick. So if the size of r, which is our vector defining the axis of the cylinder, is scaled to be equal to 1, okay, so if we scale r so that mod r equals 1, then the dot product f dotted with r is just equal to mod f cos theta, which is the component that we're interested in, okay, and so we can multiply. We can take the actual numbers and multiply that out and find what our force component is. Okay, so that gives us an example of using the scalar product or dot product. Much more important for us is the cross product. Okay, so the vector cross product is the thing that we'll use much more. So that's the second type of vector product, vector cross product. And so that's written, if we have two vectors, let's call them A and B this time, that's written like this: A crossed with B equals vector C. Okay, so the outcome of the cross product of two vectors is another vector. And I'm sure you've already done this in your maths many times. What we tend to do is write out the cross product like this: A crossed with B. Well, we can write down a determinant with I, J, and K along the top. And then we have A1, A2, A3, B1, B2, and B3. So we have the two vectors written out in their component form. And then there's a specific way of multiplying these out which gives you this result. A2 times B3 minus B2 A3 is all times by I. And then we add B1 A3 minus A1 B3 times J. And the final component is A1 B2 minus B1 A2 times K. And this comes from, there's a pattern for doing this. So the first component, for example, you have the component relating to I is this determinant, A2 times B3 minus B2 times A3. Okay, so that goes in this bracket. I'm sure you must have seen this before, right? Okay, if not, look it up on Wikipedia. There's a very good page which describes all of the intricate details of the cross product. Okay, but if we've got two vectors defined in a space and we want to find what their cross product is, this is how we can do it. It's also worth noting that A crossed with B is equal to minus B crossed with A. Okay, so we actually change, if we change the order of the multiplication, we change the sign. And if we take the modulus of A crossed with B, it's equal to the modulus of A, modulus of A times the modulus of B times the sine of the angle theta in between the two vectors. Now the I, J, and K are vectors. And specifically, what are they? Well, they create a Euclidean three-dimensional space, don't they? So they're the vectors. In the I direction, we have 1, 0, 0. So the T means transposed. Okay, so this capital T means vector transposed, doesn't it? J is the Y direction, so that's 0, 1, 0. And then K represents the Z direction, so that's 0, 0, 1. So we can take these vectors which represent the axes of our space and we can do the cross products on them. Okay, so we can actually take cross products of these vectors. And so if we do that, so if we take I crossed with j, that gives us the vector k. Okay? And that should be no surprise, should it? Because if you remember from doing this in maths, okay, the cross product of two vectors is actually gives you another vector at right angles to those two vectors, doesn't it? And you use the right-hand rule. So you remember doing the right-hand rule where you put this finger out in this direction and this one in this direction. And so if these are the two vectors you're multiplying, your thumb points in the direction of the new vector you get. Okay? So it's no surprise if we've got this Euclidean coordinate system, if we multiply two of the vectors, what we get is we get the other vector in the other direction. Okay? So that's why we can cross product our x and our y directions and we get the z direction. Okay, kind of makes physical sense, doesn't it? If we do k crossed with j, we actually get minus the I direction. Okay, and again, if we use the right-hand rule and we draw it out and think about it, what happens is we get another vector at right angles, but it's pointing in the minus I direction this time. And if we do k crossed with I, we get the j vector. And so what we'll be able to do is we'll be able to do vector algebra. Okay, so when we start working out problems of our rigid body dynamics, we'll end up with situations where we're multiplying together different vectors. Okay, and so we'll need to remember these relationships. Okay, because you'll end up with situations where you have multiple vectors cross product together, and so they actually reduce down to another vector. We're also going to represent rotation using vectors. Now, for nearly everything that we're going to do in this course, we're going to have a situation like this. We're going to have a two-dimensional space. Okay, we're going to have I in this direction, and we're going to have j in this direction. Okay, but we're going to allow a rotation at the origin. Okay, so we're going to allow a rotation around this axis at the origin. Okay, so we're going to write this, and we're going to say that k is out of the page. So what it means is that I and j are in the plane of this piece of paper, and k is sticking out at 90 degrees to the page, okay, or the plane of the piece of paper that I'm writing on. So, how do we represent rotation? Well, if we've got a shaft which is rotating, and it's rotating with angular velocity omega, and it's aligned in the direction of the I-axis, like that, then we say the rotation is omega times I. So what that means is it's the speed, if you like, of the rotation multiplied by I tells us that it's rotating in around the I-axis. Okay, and what you'll see is that we then usually write that as a vector omega underscore. Okay, so what it means is the vector omega underscore is a scalar quantity omega multiplied by a vector. And the two things, they're telling you two pieces of information. The scalar quantity omega is telling you the speed of the rotation, and the vector is telling you the direction about which the rotation is happening. Okay? And of course omega is angular velocity. So we will typically have two dimensions, 2D plus a rotation. And so it will be, just as we drew above, I and j, and we'll normally write omega like this. Okay, so our two dimensions are x in the I direction, y in the j direction, and a rotation omega around this k-axis, which we're assuming comes out of the paper. So in this case, now we have a vector. If we want to define a vector omega, it would be equal to a scalar omega multiplied by k, okay? Because now I've defined the rotation to be around the k-axis in this particular case. So we're going to do just a little bit more on this rotation concept before we move on to something else. So if we think about the rotation of vectors, okay, so we can do it like this. We define our I and j to start with. And then we think about a rotation happening, a small rotation. So if we think about what happens, this is supposed to stay at 90 degrees, so it's supposed to be the whole of the axis rotating slightly. And let's call the angle at which it rotates d theta. Okay, so we're taking a kind of differential approach here, assuming a small change, okay, which will eventually become a differential part of a differential relationship. So if we do that, then what happens is we can say that we'll get a small arc length change here, which we're going to call the change for I. We're going to get a small arc length change here as well, which we're going to call the change in j, dj. And so we're going to then use these small quantities and the arc length assumption. So we can say that the small part di is equal to d theta times 1. Okay? And that's going to be, that's a change in the j direction, so we'll multiply by j. And the 1 here comes from scaling the length of I to be equal to 1. So we're assuming that the vector we've drawn is equal to the size of 1. Okay, so when we take the arc length The arc length is the angle times the distance from the center, isn't it? Okay, we're making that equal to 1. So that's equal to so this is just essentially d theta times j. So we can then divide by dt to get a time relationship. So di by dt is equal to d theta by dt times j, which is equal to omega times j. We can do something similar for the j vector. So if we do that, we get dj by dt is equal to minus omega I. And that's a minus because the dj component is going in the minus I direction. But this allows us to make an equivalence between the rate of change of vectors and this angular rotation. So we're going to do one more concept in this lecture before we finish, and then in the next lecture we're going to start talking about some rigid body dynamics and kinematics and some examples. So we're just going to define first the concept of relative motion. And so I'm pretty sure that last year all of you were familiar with these type of relationships for velocities, that the velocity at a point A on a body is equal to velocity at point B plus the velocity of A relative to B. So what we're going to do is we're going to work in a situation where we take these components and we turn them into a translation and a rotation. So we're going to have this is equal to VB plus some vector omega, which is going to be a rotation, times a distance vector r of A relative to B. We're going to think about this as a translation plus a rotation. So, as an example, if we have a rigid body, and this example is also given in the lecture slides, and we have a point A and a point B on this rigid body. In general, we'll have some velocity VB, and we'll have some other velocity VA. And I'm sure last year you enjoyed drawing all the velocity diagrams and so on that came with these kinds of problems. So what we're going to do in the analysis of our problems is we're going to break that down, and so we're going to assume that this can be made up of two, so this arbitrary motion where VA and VB are both in different directions with different sizes, we're going to assume that that can be broken down into this, where we have, this is supposed to be the same body, but it doesn't look very much the same. So we're going to assume that both points initially are moving at VB, so that's the translation. And then there's a rotation and then that coordinate there is VA with respect to B. Okay, so that's the idea, is that if you take some arbitrary motion, like on the left, you can split it into two parts. A translation where both points are going in the same direction of VB, and then a rotation where from A relative to B, the thing is rotating, okay, and they are essentially equivalent. Okay, so that's it. Next lecture we'll do some examples to show how these things work. I'll see you then. Well, actually I'll see you on Friday.